Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on Fourier transforms. Now the nature of this particular presentation involves an application of Fourier transforms to solving partial differential equations. So we're asked to solve the following problem using a Fourier transform method. Okay, so we have a PDE here, the subscripts mean partial derivatives. We've got essentially a wave equation in one spatial dimension x. We're assuming the string or whatever's vibrating is infinitely long. U is a function of two variables, position x and time t, and U might represent, say, the deflection of the string at a point x at time t from the equilibrium position. Okay, and you have some initial condition, some initial velocity, and some of these limiting conditions. Okay, now we don't know what g of x is, but we'll just assume that it has a Fourier transform. Now, speaking of which, what is a Fourier transform? Well, I've looked at these in previous videos. The Fourier transform of a function, say, of one variable is just this integral transform. Now, it's an improper integral. You multiply through by this exponential. Remember, I is from complex numbers, and this is the transform. And playing a sort of an inverting role to the Fourier transform is the inverse Fourier transform, where you have here this thing. Now, I'm using the definition where you have the 1 on root 2 pi out the front of both the transform and its inverse. Some authors have a 1 on 2 pi here or here. Or somewhere else. So it's important that whenever you're comparing the literature on Fourier transforms, you just know which particular definition is being used. Okay, so in order to solve this problem, there's a definite algorithmic procedure involved. Okay, you transform your PDE. You produce a new problem, which is simpler, usually an ODE. You solve that, and then you take the inverse transform of that solution to recover the solution U to your original problem. Okay, now this is generally the case with transform methods, be it Fourier transforms. You may have heard of Laplace transforms. The methods are the solution methods to PDE tend to be the same. Now, a very important property when we're transforming the partial differential equation is the transform of derivatives. So how do I take a transform, a Fourier transform of the derivative of a function that we want to calculate? Okay, so let's just keep it simple. Suppose I have a function of one variable x, and it satisfies these conditions here. The transform of the derivative of f is just I times w times the transform of f. So if I wanted to write this in the hat notation, it would be something like this. And for second derivatives, very similar. You basically just multiply everything up here by iw again, noting I squared equals -1. Okay, and we're going to be interested in solutions to partial differential equations. So in that case, the derivatives that we're going to be transforming depend on two variables and they're partial derivatives. So you get the same. Now, in these cases, we're transforming with respect to x. Okay, so in the hat notation, using u hat as the transform of u with respect to x, you would get something like this. Okay. Oh, sorry. That would be a -w squared. Okay. Now, if you take the transform of a t derivative, where you're transforming with respect to x, essentially, it's just, you can basically just move the derivative or the differential operator outside the transform. Okay, so in this case it would be something like this. Okay, now where do these come from? Well, let me just briefly explain. Let's look at this one, okay? Now you could start off here, it's a little bit simpler, but let's just start off here because we're looking at partial differential equations. What you would do, you would take this derivative, you would replace f of x with that derivative, and then you would be integrating by parts once, okay? And you would use these sort of limiting conditions to get zeros in the limits in your improper integral, okay? Similarly with this one, what you would do with this one, you would plug it in there, you would integrate by parts twice, okay? And you would come up with that. Now, if I was taking, say, the transform of a second derivative with respect to t, so I'm transforming with respect to x here, you would just have a second derivative here. How do you come up with this then? Well, let's look at this one. Well, you would replace f of x with this derivative, so du dt of that, and then you would just move the dt outside the integral sign. This is a special technique called Leibniz rule for differentiating under the integral signs, and I have lots of videos on this technique. Now, instead of differentiating under the integral sign, you're going the other way. You're sort of differentiating outside of the integral sign. Okay, so that's where that comes from. So let's just call this, say, 1. And let's call this 3. Okay, so 1 follows by integration by parts, and 3 follows from Leibniz rule. Okay, so you can definitely look that up on my list of videos, and this is just integration by parts. So a couple of exercises for you to do if you're interested. Okay, let's get back to our problem. Like I said before, there's a definite method or algorithm for solving these problems. Transform the PDE, form a new problem, solve that problem, invert everything, and get back to the original setting with by producing the solution U. All right, so let's call this, on this page, let's call it, say, 1. Okay. So let's transform both sides. Okay, so let's use our transform of derivatives. So down here, so actually right down the bottom, we're going to get the following. So that's going to be on the left-hand side. And over here, I'm going to get this. Okay, so throughout, let's let u hat be the transform of u with respect to x. So let's apply transform of derivatives, TOD, to obtain the following. Okay, now we've produced another problem here, but we've only got one derivative present, a second order derivative. So actually this really is an ordinary differential equation because there's only one derivative present. Okay, so if I write it using just dashes to denote differentiation with respect to t, and I just move around, it's the following problem. Okay, So what kind of ODE is this? It's a second order linear homogeneous problem with essentially constant coefficients, because the derivatives are with respect to t, and the coefficient here is w squared. So I can solve this by looking at a characteristic equation. Now you would see this in a second course in calculus or a first course in differential equations. So the characteristic, and again I've got lots of videos on this, the characteristic equation is lambda squared from that term plus omega squared equals 0. Now throughout we're assuming omega is positive, so lambda is going to be plus or minus IW. So the complex with 0 real part. Okay? Hence the form of solution u hat is the following. Okay, well, basically it's a linear combination of cosine and sine for this. Okay. Now usually if we're solving, say, ODE, then these coefficients would be constant. But remember here, u hat is a function of two variables. So really these coefficients should depend on w. Okay, so we came up with a transform problem. We've now found a general solution to the transform problem. What we're going to do now is refine it by calculating A and B. How do I do that? Well, I'm going to use these conditions up here. Okay? All right, so now let's compute A and B from 2 and 3. Okay, so what I would like to do is get this condition and this condition in terms of u hat rather than u. So what I'm going to do is take the transform of both sides, or both sides of both conditions, and then try to determine A and B from this u hat. Okay? Two gives the following. So transform this. And we don't know what G is, but let's assume it has a Fourier transform, G hat. So if I go up to my general solution, let's call it star. So let's go up to star and plug in t equals 0. So that term's going to disappear and I'll be left with A of w times 1. And we know from over here that should equal G hat. So these things need to be equal, so A is just G hat. All right, so I know that coefficient. If I know G, I can calculate that and I know A. Okay. So similarly, let's go to 3 and take the transform of that. Now the transform of 0 is just 0. And so if I take the derivative with respect to t up here and let t equal 0, what's going to happen? Well, if I differentiate that, that's going to become sine. And when I plug in t equals 0, that'll disappear. When I differentiate that, I'm going to get WB cosine WT. So when I put in t equals 0, I'll get the following. Okay? So comparing here, what do I know? Okay. Actually, let me take that away. I know that this has to equal that, so basically B is 0. Okay, so I know what that is, it's G hat. I know what that is, it's 0. So I've now refined my solution to the transform problem. Hence, just looking for some more paper. No. Hence. Yep. So hence, the solution to my transform problem is this. All right, the last thing we want to do now is to invert the solution to my transform problem. Okay, to get the solution to our original problem. Okay. So let's recover U via the inverse transform. So how do I do that? Well, I'm going to use what's known as a shifting theorem. Okay? Basically, it tells you that if you want to take the inverse transform of this kind of complex exponential function times the transform of another function f, basically you just transform this part and the inverse transform this part and you shift it. Okay? Now it's a little bit more delicate with this thing because this is, you look at this and you go, well, that's a cosine, it's not an exponential. But I can write that cosine as an exponential or a sum of exponentials. Okay? So the first thing we realise is that I can write cosine in the following way. Okay, and you learn this in, say, first course in complex numbers. All right, so what I can do now is replace cosine WT with this and then break it up into two bits. Okay, so let's return now to my shifting theorem and look what we have. Okay, well, this and this and this and this. Okay, so I've got a G hat rather than an F hat, doesn't matter. Up here, I'll have A equals negative T, and up here, I'll have A equals T. So if I apply my shifting theorem, then I get the following. Okay, so you basically transform this and you replace x with x minus t, sorry, x plus t in that case. And over here I'll get g of x minus t. Okay, so now I have the solution to this problem up here. Okay, now you can check to see whether or not this satisfies that problem. And you basically just go through and it checks off all the parts. Now we're essentially assuming that G does have a Fourier transform here. This is a special form known as D'Alembert's, or related to D'Alembert's solution. Okay, and now you might be thinking, well, what's happening with this condition here? Well, that is a condition that is used when we apply our transform of derivatives approach. Okay, so with these, you know that you can basically transform the second derivative and the first derivative. Okay, so let me just write that down where we've gone and applied the first shifting theorem. I'm going to call it FST, the first shifting theorem. Okay, so that is the solution to this particular problem via Fourier transforms. As you can see, and as I've been saying throughout the presentation, there's a definite step-by-step approach. You transform the dE, you apply the transform derivative to produce some sort of simpler dE which you can solve. You produce a general solution, refine it, and then you invert everything via an inverse Fourier transform, and you get your result. Now I hope you found this video useful, and I hope you can join me for more presentations on Fourier transforms and their applications to differential equations. Please join me for those presentations.